there's a question that remains. How is it possible to determine whether or not a vector field F is conservative? All right, well, suppose it is known that our vector field Pi plus Qj is conservative, wherein P and Q have continuous first order partial derivatives, and there is a function F such that F, which is the vector field, is equal to the gradient F, so it's conservative. That is, P is equal to the partial of F with respect to X, and Q is the partial of F with respect to Y. All right, so because it's the gradient vector, we know that P is the partial of our function with respect to X, and Q is our partial of our function with respect to Y. Then by Clairaut's theorem, I can take the partial of P, but now with respect to Y, and that's going to be the second derivative of F, first with X and then with Y. And then if I take the partial of Q with respect to X, then I'm taking the second derivative again, but first with Y and then with X. Again, by Clairaut's theorem, we know that those two partial derivatives, or second-ordered partial derivatives, are going to be equal to each other. All right? This is basically saying F sub X, Y is equal to F sub Y, X. All right. Hopefully you understand. If not, come see me. And so again, so I can find if our vector field is a conservative vector field or not by taking the partial derivatives and setting them equal to each other. All right. So theorem f of xy is equal to pxy I plus qxyj is a conservative vector field where p and q have continuous first order partial derivatives on a domain D. Then throughout D we have the partial of p with respect to y is going to be equal to the partial of q with respect to x, where p and q's were already partial derivatives, p of x and q with y. The converse of Theorem 5 is true only for a special type of region. All right, so if we wanted to do the converse, if we said let F is equal to Pi plus Qj be a vector field on an open, simply connected region D, suppose that P and Q have continuous first order derivatives, and then we can say the partial of P with respect to Y is equal to the partial Q with respect to D throughout D, then F is going to be conservative. All right. Example 2. Determine whether or not F is a conservative vector field. If it is, find a function F such that F is equal to the gradient of our function F. All right, so the first thing that we did was we took partial derivatives. So I took my P, and I took that with the partial with respect to Y, and got e cosine y, e to the x cosine y. And then I took my partial of q, which was e to the cosine y, with respect to x, and I got e to the x cosine y. So therefore, F is conservative because their second partial derivatives with respect to the opposite variable are equal. So F is conservative. Now that we know that F is conservative, let me go ahead and lower this a little bit more. Now we need to find the potential function. So again, what we do is it doesn't matter which one we choose. We could start with the partial of x or the partial of y. So the first page I started with the partial of y. And we know that the partial of x, xy is equal to e to the x sine y. So I just actually stated what that was. E to the x sine y was our partial of x. It was our partial derivative of x to the function. So now, the next thing that we're going to do is we're going to go to the original. So this is my next step. So I take the antiderivative to get the original. All right, and so our original is going to be f of xy. When I take the antiderivative of e to the x sine y with respect to x, I'm going to get e to the x sine y. Again, that's why I chose x. I could have done it with y, but things were going to change. But if I did it with x, I knew that, hey, it's just going to stay e to the x sine y. But now I have plus gy because, again, there's a part of the function that could have been just with respect to y that I did not put. And so I need to make sure that I add that in. So plus gy. Now, I'm going to go ahead and take the derivative. So that's everything. And now from the function that I just got, I'm going to take the derivative of that with respect to y, and I get this. So f, our partial derivative of our function with respect to y is equal to e to the x cosine y plus g prime of y. All I did was take the derivative of this function, and I get that function. All right. Now, what I want to do is I want to be able to solve for g prime of y. So what I do is I take this function, and I'm going to set it equal to the partial of y that's in our conservative vector field. So e to the x cosine y. So I set those two equal to each other. When I do that, so here again, that's just showing it there. So because the partial of y with respect to x, the partial of f with respect to y is e to the cosine y, when I set these two equal to each other, I'm going to find that g prime of y is just 0. All right, well, if I take the antiderivative of g prime of y to get g of y, I'm going to get k. And so now that I have that constant k, and that's why we call it the potential function, because k can be different, and it's going to change what, our final is going to be, because we don't know what the initial constant was. It could be 2, could be 5, could be 0. So we have that k. And so then our potential function is going to be e to the x sine y plus k for the conservative vector field in which we were given.